Okay, so we're gonna go ahead and get started. So let me give you guys a little bit of info. So your lectures are gonna be recorded. I actually teach at another school, as well as there's a couple of your classmates who tested positive for COVID. And since they tested positive for COVID, they're not here. And if you happen to test positive for COVID, or you think you've tested positive for COVID, on Tuesdays when we have lecture, you don't have to be here. You'll be able to Zoom in and look at those lectures. Now, I prefer that you guys are here, the people that are required to be here. As I said, I have another class. They're online right now, so they're going to be interacting as well. They have to be online. That was part of their class. Your class is not that way. You're supposed to do it face-to-face, so I would like you guys to be here face-to-face. So you're going to kind of share me with them during this time. And it works out pretty good because we get a lot of really good questions from them as well as you guys. And so it kind of makes the experience a little more fun, and exciting. At least for me. Okay, so we're going to be going over chapter 2 today. So those who are from Harnell, CHEM2A, you guys, again, your class does not require you guys to be in the Zoom, but I strongly recommend it. So the recording will be posted, and this is for you guys as well. Recordings will be posted on Thursdays. So let's say you couldn't make it to that Zoom meeting, you were so sick, you were vomiting or whatever, you couldn't make it to the Zoom meeting, there'll be a recorded, posted on your Canvas shell on Thursdays. Now, in addition to that, you guys have lecture quizzes. Your lecture quizzes is gonna figure out how much of the stuff that I talked about that you guys obtained. So they're gonna be like 3 or 4 questions that are gonna be about the lecture. See how well you guys are paying attention and how well you're listening, and how well you guys are actually kind of thinking, okay? And so it kind of gives me an idea of what to expect. Now that goes towards your quiz grade, okay? Now Harnell, after we finish this lecture today, I'd like you guys to stay so we can go over your syllabus, okay? Are you guys there? Can you guys hear me? Or am I on mute?
Yes, we can hear you.
Excellent, good. Okay, so everybody has their lecture notes from last week? You guys are ready? So Harnell, your lecture notes are also under modules. If you go under modules, it'll be lecture notes number 2, okay? So it'll be chapter 2, PPT, I think is at the end of it. Okay, so we're gonna start off with matter and energy. And unfortunately, our display here is not working, so you guys have to keep your attention towards me. I like being the center of attention, if you can't tell. So, okay, so matter. Everything has mass associated with it, okay? Everything. So from the smallest thing to the largest thing has some type of mass that's going to be associated with it. Okay, so when we're talking about matter or mass, we're going to be talking about things on the macroscopic level, the microscopic level, and the particulate level. Macroscopic, macro, meaning big, right? Big like me, right? So macroscopic basically means that we can see it with our eyes, okay? You guys can see me, right? I'm cute, I know. Keep looking, right? So that's macroscopic. Microscopic means that we have to use a microscope to see. Right? So that's something like, let's say, a bacteria, right? A bacteria cell. Can you guys see the bacteria on your skin? No, you can't see that, right? So if we took a microscope, we'd be able to see that, okay? Particulate means that it's so small that we have to use a specialized microscope to actually see it. That's kind of like an atom or a molecule, drug, right? Okay, so because we're going to be working at the particulate level, we're talking about chemicals, right? A water molecule. Can you guys see a water molecule with your eyes? No, you can't. You can't see a single water molecule. You can see a glass of water, but you can't see a single water molecule. You can't see how it's behaving, right? So we often will have to use modeling to sit there and help us visualize it and kind of help us to see what it looks like, okay? So in chemistry, we use modeling. This here is methane, CH4. Okay, I write like a second grader, so bear with me. Thank you, thank you. He's already kissing butt already. He thinks that's the way to an A. That's not how you do it. Right? Okay, so CH4 is methane. Now, this is what we perceive methane to look like. The carbon is the center atom. The hydrogens are all bonded to that carbon, that center atom. The lines represent bonding. They're connected, right? Strongly connected. Do you guys know where methane is primarily found? The biggest source of methane. Anyone? Who said that? Cows. That is correct. Cows fart or poop, and we get a whole bunch of methane. So you guys know that if you guys fart, that's methane that's coming out as well too, right? But primarily cows. Yes, sir. Yes, but in small quantities compared to what we get from cows, right? Okay, so we will often use models, right? Like I said, so here, this is an example of a plastic model. This is often called the ball and stick model. What do you guys think is called ball and stick? Because it's balls and sticks, right? Makes sense, ball and stick model, okay? So we will often use this to show that three-dimensional display of that molecule, methane. This is called the space filling model, right? This basically shows that there's overlap between the two atoms, right? Or all of the atoms. So here's the carbon. The black represents the carbon. Often when we're using modeling, black is representing carbon, white is representing hydrogen, okay? So this is called the space fill model because you see the overlap. And it also shows us that they're sharing things, right? And what they're sharing is going to be electrons. We'll talk about that later, so don't get bogged down on that yet, okay? But the key is that we can't see a single molecule by our eye, so we will often have to use models, just pictures, to help us see it, okay? Now, these models are going to be representing the chemical symbols, right? You guys have seen the periodic table, right? So we know, just from me talking, that C here represents carbon. This H represents hydrogen. Now, you guys have access to the periodic table. You guys at home, if you guys go to P table, P table shows us the periodic table. So carbon and hydrogen on the periodic table. So we use that single letter as a symbol for that element or that atom. Hydrogen atoms, H. Carbon atoms, C. This here is called the subscript. You notice that it's a little bit lower and drop down, right? So CH4. So that subscripts let me know how many hydrogen there are in our compound. We have one carbon, it's understood there's not a one there. If there's nothing there, it's understood to be one. We have 4 hydrogens. Simple? Okay, there's something that you guys are familiar with. Water. What is the chemical formula for water? H2O. Okay, so how many hydrogens do we have? We have 2. How many oxygens? 1. So we all know that there's 2 hydrogens and 1 oxygen. So that's how we write that symbol. Okay, piece of cake, not too hard. Okay, Now, the other thing about writing our symbols is that we want to pay attention to how we write them, right? So for instance, if I write capital P, capital O. So P stands for capital P, phosphorus. Capital O, oxygen. Now, if I wrote it as PO, capital P, lowercase o, what is that? It's polonium. It doesn't mean the same thing. So we've got to be cognizant. We have to know that we writing things are in capital, right? They're both capital. That means phosphorus and oxygen. If we have a capital P and a lowercase o, that means polonium, right? Now, you wouldn't believe how often I have to tell students that on an exam, right? They're writing lowercase p, lowercase o. They're writing both of them, capital P, capital O, and they're talking about polonium. It's not the same thing. And so if somebody was trying to do an experiment and they were taking your notes and they were writing, what you wrote down to sit there and repeat that experiment, they're using polonium instead of phosphorus oxide, right? Something bad could happen. So we want to be sure that we're writing it down correctly. It sounds simple. It sounds like, oh, I understand this, but you wouldn't believe how many people always do this, right? Typically the ones that never come to class. Okay? So another example. If I wrote capital C, capital O, what's that? It's carbon and oxygen. So it's carbon monoxide. Where if I wrote capital C, lowercase o, it's cobalt, right? Cobalt's a metal. Carbon monoxide is a gas that could kill you, right? So you're saying, dude, I want you to get me some cobalt. You write capital C, capital O. Is it going to get you cobalt? It's going to give you some gas that's going to kill you, right? Big difference, okay? So we want to be aware of what we're doing, okay? Okay. States of matter. So there are 3 states of matter that we're going to be talking about technically, but we're only going to talk about 3 of them, okay? We're going to talk about the solid, liquid, and gases. So let's take water, for instance. When water is a solid, we call it what? We call it ice. When water is a liquid, we call it what? We call it water, right? When water is a gas, we call it what? We call it vapor or steam, right? So I'm going to ask you a question and I want you to think about it just for a second, and then I want you to respond. Is the chemical formula for water as a solid different than water as a gas, different than water as a liquid? What do you guys think at home? That's you at Harnell. Are you guys thinking here? Can you hear me?
Can you repeat it?
I said, is the chemical formula for water different when it's a solid, liquid, or gas?
No.
Yeah, they're all the same, right? So we know it's always going to be H2O in all cases, okay? So we know that the phases are different. Okay, so now I want you to think about it. So how do I get from water as a solid to water as a liquid? Thermal energy or temperature, right? So if I put energy in, it heats up the water or it heats up the ice. And the ice does what? It melts. So how do I get from water as a liquid to water as a gas? Okay, now that you guys thought about this, right? You guys gave it a lot of thought, right? And you gave me this really strong answer, right? Good, I want you to be confident. So now you're putting energy into the system. you're changing from a solid to a liquid to a gas, right? Now, what's happening to each individual molecule in that solid, that liquid, and that gas? So what does that mean? Did you say they'll speed up? So you're telling me, I just want to make sure, right? So you're telling me that if I put energy into a chemical compound, it's going to move faster. So are you telling me that things move? Are you serious? Are you sure? Okay, well, you guys are right? Things are moving. Even those molecules are moving. Have you guys ever been to a nightclub that is really, really packed? No, yeah? So when we're at a nightclub when it's really, really packed, how are you moving? How are you dancing? You're doing this, right? You're looking cute. You know, you're just doing a little, okay? You're just moving back and forth, right? That's all you're doing, okay? So that's kind of like that solid, right? It's very little movement. As we put more energy in, expands, we're able to get it down a little bit more, right? We can move a little bit more. Hey, you know, we can get it way more. You know, we can really get down, right? Okay, so that's kind of like water. Okay, now when there's nobody on the dance floor and it's just you can run around and jump around and act like an idiot all you want, right? That's kind of like gas. Okay, gas is going to be moving so much faster than water does. Right? Now think about this. I want you guys to think again, think a little bit. So if somebody on the right side of the room farts, does it just stay right there next to them? Right? Even though that's not the right side, that's the left side. Okay. So it moves. At some point, it's going to get to the other side of the room, right? Is it not? So that helps us understand that gas is moving, and it's moving fast. It's not slow. Okay, so this deals with the kinetic molecular theory. It basically says that everything is in constant motion, except when it's at absolute zero. Absolute zero. So what is absolute zero? Okay, so absolute zero, to translate, is the point, that's right, Robert, or Robin, the point where we're at Kelvin equals zero, which is equal to, that isn't okay, it means zero, 0 degrees Kelvin. Write that out. Kelvin is a degree of temperature that we use to represent absolute zero, because at 0 degrees Kelvin, nothing moves, which is also equal to negative 273.15 degrees Celsius. So water freezes at 0 degrees Celsius. And we're talking about negative 273.15 degrees Celsius. Could you imagine how cold that would be? It will be extremely cold, right? You're talking about freezing your pants off, right? You're literally freezing your pants off. They stop moving completely, right? We could get very, very close under ideal circumstances. Small systems, okay? So in real life, we can't, no. So we will never, somebody asked me, where is it absolute zero? So far, nowhere, and that's a good thing, because at absolute zero, everything stops. That means life is gonna stop, right? Because if you're not moving, you're not living, right? Yes. So in space, so even in space, it doesn't reach absolute zero, right? In theory, it could, right? There's a lot of things that we don't know, right? So experimentally, yeah. So in a laboratory environment in small systems, we can get that. And even then, we're minimized. We can't get absolutely there. We get really close. Truly is, yeah. Yeah, so it's extrapolated based upon. Okay. So we talked about gases, we talked about liquids, we talked about solids. We know that gases are moving and they're moving fast. They're going to also be spread apart. They're going to have force that's going to be building up with them, right? We know that liquid, right? They're going to be a little bit closer together, but they're still going to be moving. And we know that solids, they're going to be vibrating. Okay. Now there are two types of solids. We have crystalline solid and we have amorphous. So how many of you guys are sci-fi fans? How many of you guys have watched the X-Men? What is the lady that changed shapes? Mystique, okay? So Mystique is a shape changer, right? She doesn't have one shape. She could change to anything, right? Right? So she would be considered amorphous, right? Or amorph. She can change shapes. Her shape is changing. Amorphous lacks shape, okay? So it lacks organization. It's not organized. Where a crystalline structure is organized. There's a pattern to it. Does that make sense? So this illustration just basically shows you everything that we talked about. So if we think about gas, its shape is going to be variable because it really just depends on the container that it's in. And it's going to be spreading out all over the place, right? Its volume, it just depends on the container it's in, right? It's going to be random where it's going to be located, right? So it's going to be able to move. And then the speed, we know that it's going to be moving fast, right? Those particles are moving fast. We know that the spacing of those particles is going to be kind of random as well too. It's not going to be organized. Where water, well, water is going to be at the bottom of the container, right? So a cup of water is going to take the shape of that cup of water, right? Its volume is going to be constant. So whatever that volume is for that cup of water. The particle that's moving, it's going to be moving again, right? But it's going to be limited to the volume of that container, right? So the water that's moving is just going to be sitting there moving in that bottom of the container. That's it. Okay. And they're going to be interacting with each other, the particles themselves, right? And there's going to be a weak interaction that's going to be happening between each of those particles, not a weak interaction, it's medium type of interaction. That's what kind of keep water the way it is. Okay? And then if we talk about ice, ice is rigid, it's fixed. It's going to be a constant volume, right? So if we put a mole of a heart, ice in a mole of a heart, what are we going to get? That's where you guys answer. You're going to get a heart, right? Right? Thinking about Valentine's Day, my birthday, right? Just giving you guys hints there, okay? Okay, and so in that case, you're going to get vibrating of those molecules. They're going to be moving just a little bit, right? It's still going to look like a heart. You're not going to even notice that it's moved, right? You guys with me so far? Okay. Okay. So this change from a solid to a liquid to a gas, this is called a physical change, right? Because we're changing its physical form, right? Physical. But at the end of the day, we can get ice again, right? So if I melt water and I put it back in the freezer, what's going to happen? We're going to get ice back, right? So when we think about physical change, if we're able to get it back or recover it, then we know that this is a physical change or a physical reaction, not a chemical reaction. Does that make sense? Okay, good. So chemical change is different. How many of you guys cook? Anybody cook? Okay, well, we know not to eat Wilson's food, okay? So when you cook, right? So I like to cook as well, right? So I tried to make caramels. Have you guys ever made caramels? Okay, so caramels are just sugar, butter, maybe a little bit of milk, right? But that's it. The first thing that you want to do is heat up the sugar, start melting that sugar, right? Oh, of course, I forgot the vanilla. You add a little bit of vanilla too, right? So now I often will try to cook when I'm grading because that's when I get the munchies for some reason. I'm grading your guys' exams. You guys stress me out a lot. I start pulling out my hair and eating a lot, right? So I put on all my weight and everything during that time. So I will burn down a house if I'm not careful, right? And believe me, I've tried. The last time that I tried to make caramels, that's exactly what I did. These are some of the outcomes, right? So what we do initially is we take the sugar, we melt the sugar a little, right? And as the sugar melts, we start adding a little more butter and stuff like that, start mixing it up. Now, if you're not paying attention, what you're going to end up with is cold, right? So this here is an example of a chemical change, right? Because we're starting with sucrose. Sucrose is table sugar, okay? Let me give you the chemical formula for sucrose. So sucrose is C12, H22, O11. Okay. Now, if I keep cooking my sucrose and I don't pay attention to it, I'm going to get carbon and water. Carbon, C, and water. H2O. Okay. Now, this is how we write a chemical reaction. Okay. So I'm going from sucrose to carbon plus water. Okay. This line here, this little arrow, that means yield. That means I make it, right? So this side here is called the reactants. That's what's reacting. This side here is called the products. Okay, that's what I'm making, right? A product is what we get out of something, right? Okay. So is there a question? Yes. You would write C plus H2O because we're getting carbon and water, right? So if we write it CH2O, that's a different compound, right? Okay. And that's the important part when we're writing chemical equations, right? We need to know that they're separated. That plus means that they're separated, okay? So now sucrose starts off as a single molecule, right? And we're breaking it down to carbon and water, okay? Now, there is a law in chemistry. It's called the law of conservation. Law of conservation says what you put in, you must get out. So if I'm putting in this case, I'm putting in 12 carbon, 12, right? Because that's what sucrose has. It has 12 carbons. How many hydrogens does it have? It has 22 hydrogens. So let's write that down here in the middle. So we have 12 carbons. We have 22 hydrogens. And how many oxygens? 11. Okay, so law of conservation says what you put in, you must get out. So at the end of the day, my products have to add up to exactly that. Well, if I look at it, right now I only have one carbon. So how many carbons do I need so it would balance out? I'm going to need 12, a total of 12 carbons. So what I do is write in front of that carbon, this is called the coefficient. That tells me I have 12 carbons. Okay, 12 carbons. Okay, you guys are with me so far? Okay, so here, this is H2O. H2O is what? Water. So how many waters must I be making? 11, right? So if we look at it, the coefficient here is 11, right? The subscript is 2 for hydrogen and 1 for oxygen. Now we're talking about 11 waters because it's together, right? So the coefficient is talking about that whole compound together. So if we do the math, 11 times 2, 22. 11 times 1. Okay, so now I'm going to ask you, what we put in, did we get out? Okay, now this is called a balanced chemical equation because it's balanced, right? Simple, not too hard. You're going to see that a whole lot, right? Okay, so again, this is representing a chemical change. Now, I'm going to ask you a question. Again, I want you to think about this. Now, this burnt carbon and water, can you get it back? Can we make sugar from that? No, we're screwed, right? My caramels are gone, right? Won't get my nice little caramels anymore. They're totally gone, right? So I can't get it back. So that's an example of a chemical change, right? Exactly. So I changed it from sucrose to carbon and water, right? You guys got that? Okay, now we're going to test it out. We're going to see how well you guys are doing. Okay, so you guys at Harnell, the way that you guys are going to handle this is that if you take a look under your screen where it's that big green button, it'll say you're viewing or you are screen sharing Dr. Henry's screen, or you're viewing Dr. Henry's screen. You go there, there'll be a more button and it'll say reactions. If you click those reactions, so if you guys think it's a physical reactions, I want you to put a thumbs up. If you guys think it is a chemical reactions, I want you to put a heart. Okay, for you guys at home here, I want you guys, for a physical reactions, I want you guys to put a thumb up. If for a chemical reactions, I want you guys to give me a heart, okay? A heart. You'll give me a heart. They'll give me a heart because you love me. I know you guys all love me, you know. Who doesn't? You know, it's like, wait, it's hard to love something. It's hard not to love something that looks this way, you know. Okay. Okay, so let's get started. Ready? Okay. Come on. Our very first one, a log burning. A log burning. Okay, if it's a chemical reaction, it's going to be a heart. If it's a physical reaction, it's going to be a thumbs up. Okay, you got that? Okay, I just wanted to make sure everybody had me center of attention, right? Okay, so everybody says it's a heart. That means it's a chemical reaction. What do you guys think? Heart, heart. I have, okay, we have thumbs up. We have people say thumbs up. Okay, so at the end of the day, can you get that log back after you burnt it? No, so we know that that's a chemical reaction, right? So A would be a chemical reaction. Okay, our next one, icicle melting. Icicle melting. So physical reactions, thumbs up. Chemical reactions, heart. What do you guys think? Icicle melting. So if I collect it, can I collect that water and shape it as an icicle again and freeze it, right? So we know that that's a physical reaction, right? Okay, our last one. How many of you guys go to raves? None of you guys? God, you guys are so boring. Well, I guess you guys are living through the time of COVID. Maybe you shouldn't be going to raves. Okay, I get it. Okay, so those glow sticks that you see at those parties, right? You crack them, you shake them up, right? And at the end of the day, or the next day, or the next morning, or, you know, when you wake up hungover, right? So is that a chemical reaction or is that a physical reaction? Okay, it is a chemical reaction. So I should be seeing hearts, right? Because it won't start glowing again. Once it died, it's dead, right? Okay. So chances are for your quiz, you're probably going to get some of these questions again, right? It may not be exactly those, but we'll have a couple of other pictures, right? Okay, so let's get to the next topic. We're going to talk about pure substances and mixtures. So if something is pure, when we're talking about pure in terms of chemistry, we're saying that it's only that molecule or only that compound. So like pure sugar, right? Pure sucrose. Or it could be a pure element. It could be pure oxygen, right? Now, when we're talking about mixtures, mixtures are two or more substances. So how many of you guys have cocktails? Rum and Coke? Any rum and Cokes? Okay. Okay, so rum and Coke, right? It's rum and Coke, right? So that would be a mixture. Or if we want to be more exact, it's ethanol and soda, which is a mixture of a whole bunch of other stuff, right? So that's an example of a mixture. Okay, now when we're talking about mixtures, there's two types of mixtures, right? We have what we call homogeneous and heterogeneous. Okay, so when we make the reference to homo meaning the same, right? Homogeneous means that visually it looks the same throughout, okay? So I can take a little bit of it, it's gonna behave physically the same as I take another little bit of it, right? Okay, so that's homogeneous. Heterogeneous means it looks different, okay? So we'll often say it's uniform if it's homogeneous, and it's non-uniform if it's heterogeneous, okay? Okay, so how many of you guys, oh, we already asked, how many of you guys cook spaghetti? Let's be specific now. Spaghetti. Okay, everybody cooks spaghetti. So you guys should be able to answer this with no problem since the whole class cooks spaghetti. So why do you add salt to water? Okay, so you need to work on cooking just a little bit more there. Somebody take him under your wing now. Okay, you guys at Harnell, why do you guys add salt to water? So anybody who said something? So I hear so it don't stick, okay? So that's one. What was that? It boils faster? Okay, so we hear that it boils faster. Okay, what else? Okay, because it's a diuretic and it sucks in the water and it does both. It keeps it from sticking and it raises the boiling point. Because it tastes good. Okay. Okay, what do you guys think at Harnell? Jason? Since your hand is up. Are you there, Jason?
Oh yeah, sorry. Hold on.
So why do you guys think that you add salt to water? It helps it boil faster, controls the foam or froth, I'm sorry. It absorbs the salt, okay? So we have a lot of possible answers. So they're all probably true in their own right, but the chemical component, the reason why that you actually add salt to your water is so that you raise the boiling point, right? Okay, so we raise the boiling point so that the pasta doesn't get all soggy. Who likes soggy pasta? Right? Nobody. So it's actually the water is hotter. It cooks the pasta that much faster because the water is hotter and we could take it out sooner and we don't get soggy pasta, right? So, as I said, you guys were all right in your own little way. Okay? So this here basically shows you that water boiling. This is time, and this is the temperature. So as we boil water, water will boil at 100 degrees Celsius, right? And it will continue to boil at 100 degrees Celsius, and then it becomes steam, and then it's gone, right? So then it levels off, it's boiling, right? Where if we add salt to water, it will continue, depending on how much salt we add to that solution, it will continue and continue and continue going up. And that water will remain until we get enough of that water boiled out, which takes a while. So I have a question for you. I want you to think, if I boil my water long enough, will I get salt?
No.
Was that? Just salt, just salt. What's gonna happen to the water? Okay. So I'm gonna get crystals of salt in it, right? At the end. So if I boil long enough, I should get crystals of salt. So yes, yes. And we'll talk about that with nucleation. We'll talk about it later. We'll get salty air. Okay, so let me help you out a little bit. So salt doesn't melt or steam until you get to a boiling point of about 2,000 or more, right? 2,000 degrees Celsius. So, what was that? Yes, many things are possible. Yes. Yes. It's good though. No, I'm glad you guys are thinking, but that's an interesting thought. Yes. Okay. Okay. And again, we'll talk about that a little bit later. Okay. Okay. So now I want you guys to think a little bit deeper here. So is this a chemical reaction or is this a physical reaction? Okay, so we're gonna do the heart and the thumbs up again, okay? If it's a chemical, I wanna see a heart. If it's a physical, I wanna see thumbs up. Come on, you gotta be confident. Don't be shy, put it up there. Don't be shy. Come on, you guys at Harnell, you guys have to participate. Thumbs up, physical, heart, chemical. Okay, okay. Now, again, this is the moral of this is if you wanna be, okay, when is it right to be wrong, right? Okay, so I'm gonna tell you guys the honest to God truth about life. Right? I don't know if you guys have lived enough of life to really understand. The more you're wrong, the more you learn, right? If you're right all the time, then you don't learn nothing, really. You just think you're right all the time, right? So at the time to be wrong is like right now, when there's no stakes involved, right? You guys are not taking a test or anything like that right now, are you? You're not being graded on it right now, right? So this is when you want to be wrong, right? Yes. Yeah. Yeah. But you know what? Let me be honest with you, right? You think you're sounding dumb, but the things that you guys are asking, they're really enlightened, right? And you may not know how to ask them right now, but you're going to learn and you're going to get better at it. But the only way that you're going to get better at it is by being wrong, right? So it's okay to be wrong. It's okay to make mistakes. That's life, you know? The key is to learn from those mistakes, right? And also recognize that it's a mistake. You know, the one thing that I found out, I should say my girlfriend has, and he thinks he's right all the time. and he starts crying as soon as I tell him he's wrong, right? And it drives me crazy. I just want to strangle him, right? And so I'm like, okay, I have to walk out of the room and everything, right? Because I'm like, Jesus, stop crying, you know? It's okay to be wrong, okay? And I want you guys to understand that right now. And even on exams, you're going to get some of the things wrong. The goal is to try to minimize what you get wrong. You want to try to be right as much as possible on the exam, right? So don't be scared to sit there and raise your hand or say something that you think may be wrong. It's okay, you know? I'm wrong about, if you ask my girlfriend, I'm wrong about 90% of the time, right? So it's okay. Kind of get used to it. Yes, we're talking about table salt. Yes, as in sodium chloride, right? And we're not going to worry about the ionization of it or anything like that, because that just adds another little bit of a layer to it. Okay, so now the answer is this is a physical reaction, right? Because we could collect that water and put it in another jar, right? So if we had the right pot, connect the hose to it as it's steamed up, we can recollect that water, can we not? Okay, so we'll talk about this a little bit more here in a second. Okay, so let's move on. Let's see if you guys remember anything that we talked about. Okay, so if I have pure bromine and pure water, and I have a mixture of a small amount of bromine and water and a large amount of bromine and water, okay? So which one of these is homogeneous? Homogeneous. Are you sure? So what is the definition? Homogeneous? It looks the same throughout the entire thing, right? But it's a mixture that looks the same, even though I'm kind of setting you up here a little bit. Oh, actually, not on this one. There's another one I'm setting you up. Yes. Yes. So you say all of it? So a homogeneous mixture. That doesn't matter, right? What matters is that it's uniform looking. Is it uniform looking throughout the entire thing? Yeah. So this is uniform looking through the entire thing, right? So now I said a homogeneous mixture. Yes, sir. They would be homogeneous? Are you sure? Okay. So what is the definition of pure? It's just one. What is the definition of mixture? It's two or more. So if it's pure, is it a mixture? The first two are pure, and then these two are mixtures. Do you guys see the little semantics there? Those little differences. So when you guys are often taking your tests for nursing, for PCA licensing, for, I don't know, dental hygienist, right? Those are the type of questions that they get you guys on, right? You guys know it, right? You know the difference, but you guys didn't think about the terminology. What did the term say? Homogeneous mixture. So often when we're making reference to homogeneous, it refers to mixtures, okay? And that is one of the most commonly missed questions on a couple of different standardized tests. So these first two are pure, right? They're pure substances, pure solutions, right? Where these guys are mixtures, right? And they're homogeneous. Okay, so now I'm gonna ask you a really hard question. When I was a kid, was that? No, only these two are homogeneous, these two are pure, right? Mixtures. So these are pure, right? These are not mixtures, so these are just pure. These two are homogeneous mixtures, okay? Okay, so when I was a kid, we used to go like to Denny's and stuff, but it would be on special occasions because we kind of live, we're poor. We live from paycheck to paycheck, literally paycheck to paycheck. So if somebody got a new job, we go and celebrate or something like that. So, but when I go to Denny's, I would always, during this time period, this is kind of dating myself, they would actually have the jar of sugar that you kind of just dump out. And then they'd have, salt and pepper shakers, where now everything is individually wrapped, right? So I used to take the salt and dump it in the sugar and I'd mix it up, okay? So is that homogeneous or is that heterogeneous or is that pure? It's homogeneous, okay? So if I took the salt and the pepper and I mixed it up, would that be homogeneous or heterogeneous? Heterogeneous, okay? So homogeneous means, again, it means that it's uniform looking. So visually, it looks exactly the same, right? So if I have, let's say vodka and water, right? Vodka and water, would that be homogeneous? Okay. How about, let's say, orange juice and milk? Have you guys ever put orange juice in milk? So if you put orange juice in milk, it looks like it forms a little bit of a brain, right? So the layer where they mix kinda, it's like brain shape. So you'll have a little white, you'll have your orange juice at the bottom, and in the middle, you'll have like this little brain, okay? So would that be homogeneous or heterogeneous? That would be heterogeneous. Okay, so you guys know what homogeneous and heterogeneous. Now, let me give you the book's definition, right? So I like to tell you in terms that I can understand. So the book's definition says having uniform appearance and a uniform property throughout. So that represents homogeneous. Heterogeneous is having a non-uniform composition with visible different phases. So again, if we had oil and water, homogeneous or heterogeneous? Hetero. Okay. Are you guys good so far? Okay. Okay, so this here is pure water. This here is pure ethanol. This is kind of like, have you guys heard of Everclear? So it's kind of like Everclear, right? So, and this is water and ethanol together, right? Can you tell the difference? You can't, right? So now, knowing what you guys know, do you guys think we can, let's say we wanted to dilute the drinks for our friends so they don't drink up all of the alcohol. Is there any way that we can make our drink a little more concentrated or that we can get most of that alcohol back after we diluted it? What was that? Distillation. So how do you think they make Everclear? So let me give you a fact. So I actually make wine on the side, right? And so I do, a little bit of fermentation going on and stuff like that. So under the best circumstances, you're going to get about 30% alcohol. So Everclear is about 98% alcohol, right? So if I'm going from 30% to 98%, we're going to use a process like distillation, right? So if it's 30%, that means that 30% of it is alcohol, 70% of it's water. Distillation is using a physical property of both alcohol and water to sit there and separate. Okay? Distillation, we're changing the temperature. Water boils at what temperature? 100 degrees Celsius. Alcohol boils at 89.3 degrees. So how can I get something that is pure alcohol and something that is pure water? Say it again. That's right. So we're going to boil it at 89.3 degrees. Now, many people have tried this, right? And many people have blown up their houses doing this, right? So one of the things that you want to take in consideration, if you, not that you should be trying this, don't try this at home. That's what I'm going to say right now. But you want to make sure that, first off, your distillation equipment is clean. It's not clogged. That's the first thing. The other thing is that you have the appropriate ventilation. Otherwise, you're going to get a pretty nice explosion, right? Yes, sir. Exactly. That's going to be exactly the same thing. And I'll show you guys an example of distillation, a distillation column here. So not an alcohol distillation column. This is one that we use in chemistry. Believe me, I've been looking at a really nice one. One day I'm going to get a really, really, really nice one for my alcohol and to start making my liqueur, you know, on the side. So you got to make money. You know, you guys think as teachers we make a lot of money. Let me tell you, it is not as much as you guys think. So they got to make it on the side. Okay, so we can use those physical properties of different things to sit there and separate, right? So if we have iron and sulfur, and we run a magnet over, we can collect the iron and just leave that sulfur because iron is magnetic. It is attracted to the magnet where sulfur isn't, okay? You guys can actually do this experiment with cornflakes. If you get a magnet, you take some cornflakes, you crush it up, you can collect the iron in cornflakes. Cornflakes is one of the cereals that have the highest percentage of iron in it. So something you guys can do at home. Show your kids or show your boyfriend or girlfriend. Look how much iron you're eating. Aren't you proud of yourself? You're getting your iron. Okay, so the thing about mixtures, we can use those physical properties to sit there and separate those mixtures. As you were mentioning, distillation. Distillation is one of those ways that we can actually do that. Another way, how many of you guys drink coffee? Do you guys do it the old-fashioned way or do you guys use the Keurig? Of course, me too. But in the old days, we used to have to use those filters, right? Right? You use those filters to sit there and keep those coffee grinds out of it. Now, if you get the cheap filters, the coffee grinds, I mean, you have coffee grinds throughout your coffee, right? And so we know the people who had those cheap filters. So you'd have to use a couple of them to sit there and make it work out. So filtration is that process of putting a mixture of liquid and a solid through a filter and collecting just a liquid or collecting just a solid. Okay, so let me show you. This here is a distillation column. So basically we're boiling here. It vaporizes, it goes down this tube. There's a cooling tube on the outside of a tube on the inside. It cools it down those vapors. And so then we're able to collect that pure liquid, in this case, pure water. Okay. Filtration. So here we have our mixture of a liquid and solid. We pour it through this filter. And then we collect the solid up top and the liquid goes through. Just like coffee. How are you guys doing so far? Still here? Good, good, haven't lost anybody. Okay, so now we need to start talking about those pure substances, right? So I told you guys we could have pure oxygen and we could have pure sugar. Oxygen is an example of an element, right? Now, if you guys go to your periodic table, you guys have your periodic table? You guys see my periodic table? So there are 7 elements on the periodic table that are diatomic. Diatomic, di means 2, atomic means atom. So there's 2 atoms. So when we write them, when they're in their natural state, when we're working with them and they're all by themselves, they're written as, in this case, H2. For hydrogen. For oxygen, it will be O2. okay? So they're stable in the diatomic state. So those 7 are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay? You want to remember this. You guys got it? You want to remember it. Okay. Now, a quick way of remembering it. I like beer. Have no fear of ice cold beer. Okay, 1, 2, 3, 4, 5, 6, 7. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. I have no fear of ice cold beer. Okay, so those elements are diatomic. All of the other elements on the periodic table are monatomic. Well, that isn't true. There's 2 of them that are polyatomic. Those 2 are sulfur and phosphorus. Sulfur likes to be 8. It likes to have 8. So when it's in its normal state, it's most happy is when there's 8 sulfurs. Phosphorus is 4. So both of these are considered polyatomic. Those are considered polyatomic. So, right, diatomic and polyatomic. Okay. No. Ozone is one form of oxygen. Oxygen, O2, is the most common. Okay. Questions, concerns, cash. Okay. Told you, got to make money somehow. Okay, so let's start talking about these elements. So silver is an example of an element, Ag, right? Okay, so an element is going to be a pure substance that can't be decomposed to any other substances, right? So, okay, a compound can be broken down into 2 or more other substances. So for instance, H2O is a compound. It's made up of 2 or more atoms, right? 2 or more different atoms, okay? Does that make sense? So a compound is 2 or more different atoms, okay? I'm gonna add one more to it, a molecule. Well, molecule is just 2 or more, right? So if I have O2, that's a molecule. If I have CO, that's a molecule. Okay? So we're going to give you guys a run. You guys understand. So if I have just C, is that an element, a compound, or a molecule, or a combination of things? It is an element. Okay. If I have CO2, element, compound, or molecule, or a combination of both. It's a compound. What about, is it an element? Nope, it's not an element because it's not only that atom, right? Is it a molecule? It is a molecule, right? It has 1 carbon and 2 oxygens, so it's a molecule. Okay. What about H2? H2 is a molecule. Is it an element? It is an element because I told you it's a diatomic element, right? Okay, what about S8? The polyatomic element, right? Yes, it's also a molecule. So it's both a molecule and a polyatomic element. Are you with me? Yes. A molecule is two or more, right? So it could be two or more of the same atom, or it could be different atoms. Okay? Okay, so what about SO2? Compound, that's right. And it's also a molecule. It can be both, yes. So often I will say this molecule, right? Because it is a molecule. Or I'll say this compound. Okay? Does that make sense? What about you guys at home? Does that make sense? Or on Zoom?
Yeah.
Okay. Okay, so another way of looking at it is if we have a mixture is impure, right? It's composed of two different things. And we can use physical means to separate, right? And we can separate it into compounds and or elements. Where if we have a compound is going to be pure. The only way that we can separate that compound into its elements or into a elements in another pure compound is by chemical means, right? So for instance, if I have water, I can use electrolysis to break it down into hydrogen gas and oxygen gas. Sorry, I have to look at myself writing because normally I look over here. No, because that is a physical means, right? Even though you're centrifuging it, you're not going to be able to separate them, right? You have to put energy to break those bonds, right? So if you think about it, if you put centrifuge, water in a centrifuge, all you're going to end up with is water everywhere, right? That's it. Yes, yes, you can use a laser to separate them because you're putting energy to break the bonds. That's different, okay? Any other questions? Okay. So this is an example of compounds and elements. So copper pennies, although we know now that the pennies today aren't pure copper. They have a little bit of nickel in them. We have copper wire. We have iron bolts. We have lead weights. We have silicone wafers. We have graphite in our pencils. And we have silver. And these are examples of compounds, baking soda, chalk, compounds that we see every day. So every day we come across various compounds and there's elements. Yes. Okay, repeat that one more time. No, actually, they're going to be a little bit different, okay? So because it's not truly a compound, they'd be considered an alloy, okay? So you're doping those metals. Okay. So basically that means that you have primarily it's one thing and you just add a little bit of something to make it behave slightly different. Okay. So it's not truly a compound. Even though that they're interacting, that interaction is a metallic type of interaction. It's a little bit different. And again, we'll talk about that a little bit. Okay, so we already talked about how we would go about naming those elements, you know, the capital letter and the lowercase letter. We've talked about what that subscript is, right? And the fact that that's a ratio, right? We always know that water is always going to be a 2-to-1 ratio, 2 hydrogens to 1 oxygen. Right? An atom is going to be the smallest particle of an element. Okay. And we've already talked about a molecule, the smallest unit particle of a pure substance. Okay. The law of definite composition. So this is a law that basically says that regardless of how much water you have, that chemical formula is always going to be the same. It's always going to be H2O, right? It's always going to be water. That ratio is always going to be the same. 2 hydrogens to 1 oxygen. So regardless of how much you have, it doesn't matter. So if you have 1 molecule or if you have a glass of water, it's going to be the same. Okay. One thing that we kind of have to understand is electrostatic forces. So basically positive and negative charges. How many of you guys dated in high school? You said no every time. Okay, a couple of you guys, right? How many of you guys dated in college or are dating in college? Okay, you never know. Chemistry may happen in the classroom. You never know. It's chemistry, right? Okay, anyway. So when you guys were in high school, I don't know if you guys were the good boy or the bad girl. I'm taking a guess on you. I think I have an idea if you're the good girl or the bad girl. Oh, yeah. Stephanie. No, Stephanie. You're a good girl. Sure. Okay. So, no, and I think I have a good idea about Heidi as well, too. So since you brought it up, you know. Okay, so now we know that when we're in high school, if you were the good girl and you were seeing that bad boy and that bad boy came and asked you, hey, what's your name, right? You're like, oh my God, you run home and you're like, mama, guess who talked to me today, right? And you tell mom, oh, it was Johnny. And your mom says, Johnny from up the street, that little gangster, that thug, right? Mama, he's not a thug. I love him, right? So we know that opposites attract, right? We know that in life and in chemistry, opposites are always going to attract. So if we have a positive and a negative, they're going to come together, okay? Now, they're going to come together perfectly if they're both the same charge, if we have 1 positive and 1 negative, right? Now, if Johnny is a really, really bad boy and you're just a little bit of a good girl, you may not be able to handle Johnny, right? So Johnny may need another positive to kind of add on. And we'll talk about that a little bit later, right? Okay. So the key is that opposites, positive and negatives, are going to attract. But if you get a positive and positive together, it's going to repel. Okay. So positive and positive come together, they're going to repel. They're going to push away from each other. Negative come together, they're going to push away from each other. But a positive and a negative, they're going to come together. Okay, are you guys with me? Okay, so you can actually test this out. So if you get a glass rod and a couple of little rubber balls, right? So if you take your glass rod and rub it with a silk cloth and you touch one side, right? One of the balls, it's going to actually attract, okay? If we touch both sides, it's going to repel, because what we're doing, we're putting a positive charge on each of those balls. So each of those balls are going to come together and it's going to push away from each other, right? Because positive, positive. Now, if we take that glass rod and rub it with a fur, it's going to give us a negative charge. And we touch the ball, right? We touch one ball with the silk rod, touch one with the fur rod, it's going to come together, it's going to be attractive. If we touch them both with the fur rod, it's going to be two negatives, it's going to push apart. Okay, so that's one thing that you guys can just test out. I don't know how many of you guys have fur at home. I don't have a fur, because I don't really like fur too much anymore. Usually, if I kill an animal, I'm going to be eating that animal. Okay, so we talked about chemical equations. So we know that this side of the reaction, we have the reactants. This side, we have the products. Okay? Reactants, products. We know that this line here represents yield, or to make, right? It means yield, like the yield sign. So we yield, we make it, okay? We've talked about coefficients, right? So coefficients lets us know how many of that molecule that we have. So here we have two waters. Two waters will make two hydrogen gas and one oxygen gas. Okay. Energy. So energy is defined as the ability to do work or to transfer heat. Okay. So if something is exothermic, exo meaning out, exothermic meaning that energy is being released. Okay. So if we take a look and we burn that log, you stand next to it, do you feel heat? So is that endothermic or exothermic? It's exothermic. Okay. So have you guys have had those cold packs where like they say you bump your head and everything like that, or twist your ankle? Wilson knows about those, right? So those cold packs, they get cold, right, as we mix those chemicals. So would that be an endothermic reaction or would that be an exothermic reaction? It'd be endo, because it's taking in heat from the environment, so it's getting cooler, right? Okay. So kinetic energy is the energy associated with movement. As I said, endo, we're putting energy into the system. Okay. Potential energy. You guys have the potential of getting an A in this class, right? So everybody right now has an A. You guys are at that highest point, right? So potential energy is the energy due to the arrangement, right? So you guys enrolled in a class right now, everybody has an A. So you still have the potential of getting an A. Now, if you continue to do work, right, put energy into the class, you should get an A, right? But if you stay at potential, then eventually it's going to drop down. You don't do anything, right? So potential energy has to be converted to kinetic energy. Now, overall, energy is conserved. Law of conservation again. Okay, so energy can be related to mass. So Einstein basically says E equals mc squared. Okay, now I want you guys to give this a little bit of a thought. If I have my water bottle here and I get really mad at Jace, right? Mad. And I toss my water bottle at Jace and I hit him in the head. Okay. Now, if I toss it, just toss it to him lightly, is that going to hurt as much as if I get really, really mad at Jace and I just chuck it behind as well as I can? Which is going to hurt worse? When I really, really chuck it. Why? What was that? More force and
Speed.
more kinetic energy, right? So more kinetic energy, more force, and it's going faster, right? So if we look at this equation, C represents speed, right? M represents mass. So this weighs the same either way, whether I toss it or if I chuck it. The difference is that speed. The more speed, the more movement, the more energy. Okay, so if a molecule is moving fast compared to if a molecule is moving slow, it's going to have more energy. Okay, you guys get that? Okay. Now, let's say I take Bertie and I take my bottle. All right, throw them both at the same speed. I think which is going to have more energy? Why? Because there's more mass, right? Yes. Yes, if the speed, yes. So you can compensate, yes. So if we're saying that we want the same, this is actually brings me to my next point. If I have the same amount of energy, right? I can compensate by either speeding something up or slowing something down, right? Okay, so if we look at this, we want constant energy. If I increase the mass of something, so mass is going to increase. So what has to happen to the speed if I want constant energy? Are you sure? What was that? Somebody said over here. I heard decrease. You said decrease. Okay, so the speed has to decrease to compensate, right? If we're keeping constant energy. Okay, so we're saying that E is going to be exactly the same. So if I'm increasing the mass, if I'm going from 1 to 2, so that means that for it to be exactly the same, that means that the speed has to slow down. Okay, so that would mean that mass and velocity or speed are indirectly proportional. Indirectly proportional, opposite direction. Okay, where energy is directly proportional with mass and speed. So if I increase the mass, the energy is going to go up. If I increase the speed, the energy is going to go up. Okay, so energy would be directly proportional to mass or speed. But okay, how are you guys doing so far? I lost you? Okay, let's go back. Okay, so, yes. That's right, exactly. So if I throw my stuffed bird hard enough, even though it's lighter, right? I can give him as much of an impact as I gave him with this water bottle if I throw it harder, faster. Speedier, faster, yes, speedier, yes. Even though it's smaller and lighter, right? Even though it's smaller and lighter, I can hit him with just as much force or just as much energy as I hit him with this if I throw it fast enough. Yes. That's right. Yes. Okay. How are you guys doing at home? You guys still there?
Yes.
Yes? No? Maybe?
Yes.
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 Okay. So does that help you guys, or do you still need a little bit more?
A little bit more.
They go up together, right? So if he gets lower, let's say it weighs less, right? Then you're going to have less energy, right? So let's say we keep the speed the same, right? We keep the speed the same, and then we have a smaller thing that we're throwing at the same speed, the energy is going to be less. Does that make sense? So that means that they're directly proportional. Energy goes up if it goes up in mass. Energy goes down if it goes down in mass, right? Okay. So that means directly they're same directions, okay? So energy goes up if mass goes up. Energy goes down if mass goes down. Is directly proportional. Okay. Okay, so that kind of brings us back to the law of conservation. Law of conservation basically says that the total quantity of mass and energy in a universe is fixed and it doesn't change. So that means the total mass of the reactants in a chemical reaction is going to be equal to the total mass of the products. What we put in, we got to get out. Okay. And law of conservation of energy says that the quantity of energy within an isolated system doesn't change. So if energy doesn't change, then what must happen? How do we get light? How do we get light? Because isn't light energy? Okay, but then how do we get electricity that's running through those bulbs? So are we in the right place? I don't see solar panels on this place. You said a coal factory, yeah. The power grid. So, and most of our power grid is made up of what? Our fuel, what is, I'm sorry, oops. Gas, right? So we get a lot of our power from gas, right? We're not utilizing as much of the sun now. I mean, we do have that sea of things now, but before we weren't. And we're just starting to tap into that, right? So, okay, so that brings us to this point. Energy is conserved. So we're starting off with one form of energy and we're converting to another form of energy, okay? So we're starting out with natural gas. Unfortunately, we use a whole lot of natural gas. That natural gas gets those boilers burning. That causes pressure to build up. That pressure causes, I guess I should erase that. It causes the turbine to move. So that causes kinetic energy to form, right? So we're going from a chemical form of energy to a kinetic form of energy, right? Because of the gas. And that gas is moving the turbine, causes the turbine to move. That turbine is then causing that generator to start producing those electrons. Those electrons are then being transferred to our lights, to our ranges, to our TV. At the end of the day, the energy that we started with, that gas energy, has to equal the energy that we're getting from our TV set and our range and our lights. Okay, because energy is conserved. You guys get that? Good. Welcome to chemistry. Okay, so that is the first lecture. Are there any questions so far? Chapter 2. Okay, so a couple of things that I want to talk to you guys about before I let you go this class, but Darnell, I want you guys to stay around so I can go over your syllabus. Is on, did everybody get registered for Chem 101? Okay, everybody's done the very first assignment for Chem 101. Everybody started the second assignment for Chem 101. Good. Okay, so just in case, because I know some of you guys are, I'm so shy. If you're one of those shy people, what you guys want to do, you want to go to modules. You want to go to getting started. When you go to getting started, oops, I guess I should probably show you. Okay, you want to go to modules, you want to go to getting started, and then you want to click CHEM 101. When you click CHEM 101, what was that? Yes, the first one was just a yes or no question. Yeah, you should be able to get full credit for that. I would hope. You failed? Yes, you can start on the chapter 2. We went over today, so get started. So if you go to CHEM 101, it'll actually take you to CHEM 101. You guys are going to have to register. Now, as a student, if you're having trouble finding your homework assignment, you want to make sure that you go to the homework tab. All your homework assignments are going to be there. I have a lot of homework assignments already. So go ahead and get started with those homework assignments. Get started in advance. And it's a really cool little system because you can start today, do 2 or 3 problems, and then tomorrow you can do 2 or 3 problems until you get all 30 done, right? And so you could always come back and get it done, okay? As long as you get it done before it's due, okay? Good? Okay, so you guys have 1 more week till your trial is up. Parnell, you guys have 2 weeks before your trial is up, okay? Okay, so next week you guys are gonna wanna pay for it, okay? Otherwise, it doesn't show me your grade and then it gives you guys zeros. Hey, 43 bucks. Come on, you cut off Starbucks for a week? Well, we can make arrangements for you. There's always ways of getting money, you know, so. It's a one-time payment, one time. It's only one time, yes. It's not a monthly payment, it's a one-time payment. It's like $43.99. Okay, and the other thing is that you guys want to download the app on your phone so you guys can use it in the toilet. Okay? Okay, so you guys at Kalinga, I'll see you guys on Thursday for lab. Okay, Harnell, stay around and we'll talk about your syllabus real quick.